March 15th, 1898, Hartford, Connecticut. Francis Pratt stood in the machine shop that bore his name, examining a rejected steam engine cylinder with the methodical attention that had defined 40 years of American manufacturing. The morning light, through factory windows, illuminated the problem with brutal clarity, a bore diameter measuring 12.515 inches when specifications demanded 12,500 inches, 15 thousandths of an inch. In European workshops equipped with Swiss micrometers and German precision measuring instruments, such a deviation would have been caught during machining. In American shops operating without that centuries-old infrastructure, it represented the third rejection that week. Before we continue with the video, if you're listening right now, help me prove something wrong. My wife said I wouldn't even reach 1,000 subscribers, but I believe stories about old machines like this deserve to be heard. Help me show her that these videos matter. Please subscribe to our channel, and let's keep these old machines' legacies alive. Across the Atlantic, British and German machinists achieved consistent tolerances of 1,000th of an inch through measurement systems developed over generations of guild knowledge. Sir Joseph Whitworth's 1841 standardization of screw threads had created an entire ecosystem of calibrated instruments, micrometers, gauge blocks, precision squares, that every European apprentice learned to use during their 7-year training. American machine shops had no such foundation. Imported micrometers cost $40 each, equivalent to 3 months' wages for a skilled machinist. Temperature variations in American factories rendered precision measurement unreliable anyway. Summer heat expanding metal parts, winter cold contracting them, rendering morning measurements invalid by afternoon. Each shop developed its own measurement standards with no interchangeability between manufacturers. Parts machined in one facility required, custom fitting in another. European observers visiting American factories in the 1890s wrote with mixture of fascination and condescension about what they witnessed. The Americans possessed ambition without discipline, machinery without precision, production without the systematic measurement that defined proper engineering practice. A German technical journal published a dismissive assessment that same year, noting that American manufacturers attempt to substitute mechanical complexity for craft skill, producing machinery of impressive scale but questionable accuracy. The prediction seemed mathematically certain. American manufacturing would remain inferior until it developed the measurement infrastructure that European workshops had built over centuries. What those European observers never understood was that Americans weren't trying to match European precision through measurement. They were engineering around measurement entirely. Francis Pratt and his partner Amos Whitney had recognized the fundamental problem a decade earlier. If you cannot measure precisely, build machines that repeat precisely. The Shaper principle emerged from this insight: straight line motion enforced through mechanical linkages rather than verified through measurement. A reciprocating ram driven by crank mechanism, the tool cutting on forward stroke and lifting on return, the table advancing in precise increments through gear reduction. No measurement required during operation. The machine itself enforced accuracy through mechanical advantage and geometric certainty. The mathematics revealed the engineering genius. A 20-to-1 gear reduction meant hand crank movement of 1 inch translated to table movement of 5/100ths of an inch. A machinist could feel 1,000th inch differences in resistance through the crank handle. Temperature-compensated cast iron construction minimized thermal expansion that plagued precision measurement. The machine didn't measure parts. It produced identical parts through mechanical repetition that made measurement unnecessary during production runs. Cincinnati Milling Machine Company's Frederick Geiger had demonstrated similar principles with his 1884 universal milling machine. The dividing head allowed precise angular positioning through gear ratios, creating bolt hole patterns and gear teeth without measuring individual positions. Set the mechanism, operate the machine, trust the geometry. British engineering magazines mocked what they termed American obsession with special-purpose machines. True precision, they argued, required skilled handwork and constant verification. A $1,200 mechanical shaper represented wasteful complexity when a $150 set of hand tools and a properly trained craftsman could produce equivalent results through traditional methods. The cost objections carried weight in economic analysis. European craft traditions emphasized incremental tool purchases and decade-long apprenticeships that distributed training costs across generations. American manufacturers proposed massive capital investments in machinery to compensate for skilled labor shortages and measurement infrastructure gaps. The prediction from established engineering authorities seemed inevitable. American shops would fail when projects required tolerances tighter than mechanical slop in their elaborate machines would allow. But mechanical advantage through gear reduction wasn't subject to mechanical slop. A properly designed shaper with 20-to-1 reduction and temperature-stable construction could achieve 0.002 inch repeatability without ever measuring a single dimension during production. One shaper could produce 50 identical parts, where hand methods produced 50 similar parts requiring individual fitting. Frederick Taylor would write in 1906 that the shaper transformed American manufacturing from craft to system, recognizing how mechanical precision replaced measurement precision as the foundation of interchangeable manufacturing. Within 30 years, American mechanical shapers would be producing artillery shells to tolerances European hand methods couldn't match. Within 60 years, those same machines would be declared obsolete by technologies that couldn't match their longevity. But in that spring of 1898, Francis Pratt examined his rejected cylinder and calculated not measurement solutions but mechanical ones. The precision problem wouldn't be solved by importing European instruments. It would be solved by building machines that made European measurement methods irrelevant. April 3, 1917, Watertown Arsenal, Massachusetts. The crisis arrived through coded telegram from British Munitions Ministry headquarters documenting what battlefield commanders had suspected for months: artillery shells failing at 15% rate due to dimensional inconsistencies. British manufacturers using traditional hand machining methods couldn't maintain tolerances under wartime production demands. Each shell required precise bore dimensions for proper rifling engagement, with deviations beyond 0.005 of an inch causing catastrophic accuracy failures or premature detonations. American arsenals received specifications demanding 500 shells daily with rejection rates below 1%. European measurement-based manufacturing had collapsed under mass production requirements. The American solution arrived on flatbed rail cars, Cincinnati No. 3 shapers, each weighing 4,000 pounds and capable of operations that required no precision measurement during production. Installation crews bolted the machines to concrete foundations and connected 5-horseport electric motors while ordnance engineers prepared cutting tools and set up specifications. Within 72 hours, the first shaper was cycling through artillery shell production at 18-hour shifts. The Whitworth quick return mechanism provided 2-to-1 ratio between cutting stroke and return stroke, the ram traveling forward at 30 feet per minute while the single-point cutting tool removed steel, then snapping back at 60 feet per minute while the ratchet feed advanced the work table by preset increment. No coolant needed, chip evacuation through gravity, the entire operation monitored by machinists who never touched a micrometer during production runs. Each shaper produced 500 shells per 8-hour shift with rejection rate of 0.008%. British observers documented the operation with undisguised amazement, requesting detailed specifications for machines that achieved through mechanical repetition what European craftsmen couldn't accomplish through skilled measurement. The shells leaving Watertown Arsenal maintained bore tolerances of plus or minus 0.002 of an inch across production runs of 10,000 units, all without individual verification. The machine's mechanical advantage enforced consistency that human measurement and hand filing could never replicate under production pressure. The deep mechanics of shaper operation revealed engineering sophistication that external observers rarely appreciated. Tool geometry determined everything. Single-point cutting tools ground to specific rake angles, optimized for ordnance steel. The cutting edge approached material at 12-degree positive rake, shearing rather than crushing metal fibers, producing surface finishes of 125 microinches adequate for all but the most demanding applications. Cutting speeds of 30 to 40 feet per minute for mild steel represented optimal balance between tool life and material removal rate. Push too fast and cutting edges dulled within minutes. Too slow and production rates made delivery schedules impossible. Master machinists accumulated decades of knowledge about these relationships, understanding through experience what engineering handbooks couldn't fully quantify. Comparison with alternative methods made the shaper's advantages mathematically undeniable. Hand filing achieved approximately half a square inch per hour with inconsistent depth that required constant verification. A shaper removed 15 square inches per hour, repeatable to 0.002 of an inch without measurement. Larger planers handling 10-foot beds achieved 200 square inches per hour on locomotive frames and ship components, their massive rams driven by the same mechanical principles that powered smaller machines. The institutional knowledge required for optimal operation passed from master to apprentice through observation rather than formal instruction. Reading the cut-through sound and vibration, knowing when to advance feed versus reduce speed based on material hardness variations, identifying steel alloy composition by spark pattern, and cutting resistance. These skills required 30-year careers to fully develop, but produced capabilities no measurement system could replace. Ford Motor Company's Highland Park plant operated 47 shapers simultaneously for automotive manufacturing by 1923. Engine blocks, transmission housings, crankshaft journals, components requiring precise dimensional relationships but not complex curved geometry. Each crankshaft journal received 3 passes: rough cut removing bulk material, semi-finish pass, approaching final dimension, finish pass achieving surface specifications. No measurement between passes, mechanical stops set depths, the machine's repeatable motion ensuring each pass removed exactly the predetermined amount. Baldwin Locomotive Works deployed a 200-ton planer cutting 40-foot frame rails in single 8-hour cycles, achieving 0.005 inch straightness over entire length. The setup required master machinist expertise, but once configured, the machine operated for weeks producing identical results. Tool and die manufacturing revealed the shaper's unique geometric capabilities. Internal corners impossible for rotary milling cutters, the shaper's reciprocating motion reached into confined spaces where rotating tools couldn't access. Cutting hardened steel that defeated hand files, the carbide-tipped tools advancing through material that would have required hours of manual grinding. Dies for automotive stamping, molds for casting, precision jigs for assembly, the shaper cut master patterns that defined American mass production capability. By 1935, over 50,000 mechanical shapers operated in American factories. Cincinnati Shaper Company alone maintained 12,000 machines in active service, with average operational lives extending 40 to 50 years. Some machines manufactured in the 1890s remained in production use during the 1940s, their cast iron construction and mechanical simplicity enabling generational service. Purchase prices ranged from $800 to $2,400. Depending on size, annual maintenance costs of $50 to $100 covered oil changes and occasional bronze bushing replacement. Energy consumption from 2 to 5 horsepower electric motors represented negligible expense. Operator wages of $1.20 per hour in 1935 rates. No software, no computers, no digital systems to fail or become obsolete. A shaper built in 1910 could produce parts to 1950 specifications with nothing more than routine maintenance and periodic way scraping to restore geometric accuracy. December 8, 1941, the day after Pearl Harbor, American military planners faced mathematics that seemed impossible. The nation needed to produce 50,000 aircraft annually, up from 2,000 the previous year. Each aircraft required over 400 precisely machined parts. European advisors recommended establishing measurement standards first, estimating 18 to 24 months to train inspectors and distribute calibrated instruments across new factories being built in farmland from Michigan to California. The American response came through actions rather than debate. We don't have 18 months. Willow Run Bomber Plant outside Detroit began construction in April 1941, with Ford engineers specifying 167 shapers before the building itself was completed. The strategy violated conventional manufacturing wisdom that emphasized skilled labor and precision measurement. Ford's approach assumed the opposite. Mechanical systems could compensate for operator inexperience if the machines themselves enforced accuracy. Each shaper would be configured by a master machinist, then operated by workers with just 2 weeks training. The machine would store the precision, the operator would simply feed material and trigger the cycle. Engine mounts for B-24 bombers demonstrated the system's capability under wartime pressure. Each bomber required 1,200 engine mounts machined from aluminum castings. The IE critical dimension demanded bolt hole spacing of exactly 6.250 inches with tolerance of plus or minus 5 thousandths. Traditional manufacturing required skilled machinists measuring each part with calibrated instruments. The shaper achieved specification through mechanical stops: index the part, make the cut, rotate 90 degrees, make the next cut, repeat until complete. No micrometer measurement during production. The rejection rate measured 1.2% compared to 8% predicted for methods requiring constant measurement verification by semi-skilled workers. Landing gear trunnions presented even more demanding requirements. 4340 steel heat, treated to 40 Rockwell C hardness, surface finish of 125 microinches for fatigue-critical applications. The shaper consumed 8 hours per part, running through the night with automatic feed advancement requiring no operator attention. Carbide-tipped cutting tools. Advanced through hardened steel at 25 feet per minute, the rhythmic clank of the ram's return stroke echoing through factories operating 24 hours daily. Workers arriving for morning shift found completed parts waiting for inspection, machined while the factory slept. British aircraft production provided stark contrast in manufacturing philosophy. Spitfire factories employed 22 inspectors per 100 workers, each part verified with calibrated instruments before advancing to next operation. Inspector training required 6 to 12 months of specialized education. Production peaked at 320 aircraft monthly in 1944, despite employing the most skilled workforce in European manufacturing. American B-24 production at Willow Run reached 650 aircraft monthly that same year with just 3 inspectors per 100 workers. Random sampling verified 1 part in 50. The system relied on machine capability rather than operator skill, or constant measurement. The productivity numbers revealed the fundamental difference in approach. A single shaper operator with 3 weeks training produced 40 parts per 8-hour shift. Equivalent hand machining by craftsmen with 3 years' experience yielded 8 parts per shift. The 5-to-1 productivity advantage emerged not from working faster, but from eliminating measurement and fitting operations. Parts came off shapers ready for assembly because mechanical repetition guaranteed dimensional consistency that hand methods with constant verification couldn't achieve under production pressure. The master machinist role evolved into something European craft traditions had never imagined. Instead of producing parts themselves, masters configured machines for semi-skilled operators. One master could set up 20 shapers, each then operated by workers who understood basic procedures, but possessed no deep machining knowledge. Setup consumed 2 to 4 hours per machine for new part geometry. Once configured, the shaper ran for weeks, producing identical parts, while the master moved to other machines requiring expertise. Tool grinding emerged as the only precision measurement in the entire system. Each shaper consumed 2 to 3 cutting tools per shift as edges dulled from continuous use. Toolroom workers reground cutting edges to specific geometries using optical comparators, the single point where measurement mattered. 15-minute cycles removed tools, ground fresh cutting edges, verified angles, and reinstalled for continued production. The cutting tool geometry determined surface finish and dimensional accuracy. Everything else was mechanical repetition. The reliability achievement under wartime conditions validated every aspect of the shaper-based system. Machines ran 24 hours daily, 6 days weekly with maintenance performed Sundays. Mechanical failure rate measured 0.3%, one machine down per 300. Operating: no computers to crash, no software to debug, no digital control systems requiring electronic technicians. When problems occurred, shop mechanics with basic mechanical knowledge could diagnose and repair using standard tools and replacement parts available from industrial suppliers. Between 1942 and 1945, American shapers produced over 2 billion precision parts for military applications. Aircraft components, naval vessel fittings, tank armor connections, artillery mechanisms, the mechanical precision that European observers had dismissed as inadequate in 1898 now sustained the largest military production effort in human history. The very mechanical simplicity that made shapers invincible during wartime would be declared obsolete within 20 years by engineers who confused complexity with capability. September 1952, MIT Servomechanisms Laboratory, Cambridge, Massachusetts. John Parsons stood beside the first numerically controlled milling machine watching punch tape, feed-through readers that translated holes into machine motion. The promise seemed revolutionary. Program complex curves impossible for mechanical linkages, eliminate skilled setup requirements, achieve consistent results regardless of operator experience. Engineers wouldn't configure machines through mechanical adjustments. They would write programs. The machine would think. The operator would simply load parts and press the start button. The United States Air Force committed $3.5 million to the project, equivalent to $40 million in contemporary currency. The rationale focused on aircraft geometry becoming too complex for manual methods. Turbine blades with three-dimensional curved surfaces, wing structures with compound angles, components that shapers with their straight-line reciprocating motion couldn't approach. The marketing message crystallized into a single dismissive phrase repeated in engineering journals and trade shows: shapers are limited to straight-line cuts. Modern manufacturing needs arbitrary geometry. The 1960 price comparison revealed the first indication that numerical control represented something fundamentally different from previous machine tool evolution. A Cincinnati mechanical shaper with 18-inch stroke sold for $3,200. The Milwaukee Matic 2 NC milling machine cost $87,000. The ratio of 27:1 seemed justifiable if the new technology delivered proportional productivity improvements. But operating costs told a different story that machine tool salesmen rarely emphasized during demonstrations. The mechanical shaper required 3-horsepower motor consuming 15 cents per hour in electricity. Annual maintenance of $200 covered oil changes and occasional bronze bushing replacement. Cutting tools cost $400 yearly. The operator earned $4.50 per hour with semi-skilled classification. Total annual operating cost for 2,000 hours calculated to $10,250. The NC milling machine demanded 15-horsepower motor plus hydraulic systems and electronic controls, consuming $1.20 hourly in energy. Maintenance escalated to $3,500 annually for hydraulic seal replacement and electronic component repair. Complex tool changers increased tooling costs to $2,800 yearly. The programmer required engineering degree commanding $8.50 per hour. Punch tape system maintenance added $800. Total annual operating cost reached $24,500. The new technology cost 240% more to operate while handling the same flat surface work that shapers had performed efficiently for 60 years. The productivity claims deserved scrutiny that few purchasing managers applied. CNC proponents advertised complex parts finished 10 times faster than manual methods. Reality revealed that 85% of manufacturing work involved simple geometry that shapers already handled efficiently. For the 15% of truly complex applications, CNC demonstrated 3 to 5 times improvement, but companies were replacing all their shapers with CNC based on capabilities needed for a small fraction of production volume. The dependency creation began subtly, then accelerated as numerical control evolved. A mechanical shaper needed electricity, cutting tools, an operator with 2 to 4 weeks training, and annual maintenance consisting of filing ways and replacing oil. That complete list sustained production for decades. The CNC machine required electricity at 5 times consumption, expensive carbide insert tooling, a programmer with engineering background, punch tape systems or paper tape readers, hydraulic systems with contamination-sensitive clean oil, electronics boards with no repair manuals requiring complete board replacement when components failed. climate control because early electronics failed above 85 degrees Fahrenheit, and vendor support contracts costing $4,000 to $8,000 annually. The vulnerability multiplication became apparent only after factories committed to the technology. Shaper failure modes included motor burnout, broken gears, and worn ways, all repairable by shop mechanics using standard tools. CNC failure modes expanded to include tape reader malfunction, servo drift, hydraulic leaks, electronics failure, power surge damage, and program corruption. Average shaper downtime measured 4 hours annually. Average CNC downtime in 1975 reached 120 hours yearly. Shaper availability of 99.8% compared to CNC availability of 93.2% meant the expensive new technology spent nearly 7% of production time inoperable. General Motors' Lordstown plant provided case study and promised versus delivered performance. The 1970 purchase of 43 Cincinnati Millicron CNC machines to replace shapers and manual mills came with projections of 40% productivity increase. First-year reality documented productivity gains of 12% on complex parts, representing 15% of production volume, but productivity decreased 8% on simple parts, comprising 85% of volume due to programming overhead that mechanical machines didn't require. Maintenance costs ran 340% higher than projected. Downtime issues forced retention of 12 old shapers as backup production capability when the advanced machines sat idle awaiting repair. The industry pressure to adopt CNC intensified regardless of operational results. Machine tool salesmen warned that competitors were modernizing. Engineering journals published articles dismissing mechanical machines as obsolete technology. Young engineers trained on CNC in universities viewed shapers with contempt reserved for ancient artifacts. Nobody questioned why factories should replace machines that still worked perfectly and cost substantially less to operate. A few resistors remained. Small job shops claimed they couldn't afford CNC and would continue with shapers. Tool and die makers recognized that for one-off custom work, CNC setup time negated any speed advantage during actual cutting. A machinery rebuilder observed in 1978 that he was buying 40-year-old shapers for $500, rebuilding them for $2,000, and selling them for $8,000 to shops that had tried CNC and returned to mechanical reliability. The shapers being scrapped in 1975 would outlive the CNC machines replacing them, but that discovery awaited another 20 years of expensive lessons. January 14, 2024, mid-size job shop in Toledo, Ohio. The modern CNC machine occupied premium floor space with its sheet metal enclosure and touchscreen interface, a 2120 Haas VF4, purchased for $89,000. The machine required Windows-based control system, Ethernet connection for program transfer, and cloud-based programming software subscription costing $3,200 annually. Shop Network connected the CNC to CAD/CAM workstations, inventory management databases, and quality control systems. The integration promised efficiency through digital coordination. It delivered vulnerability through dependency multiplication. The technology stack revealed layers of failure points that mechanical machines never imagined. Control software operated as proprietary code with no source access. Post-processor software for converting generic programs into machine-specific commands cost $1,800 as separate purchase. Simulation software preventing costly crashes required $4,500 annual subscription. Any component failure rendered the entire machine inoperable. Network dependency extended beyond the shop to Diaz. Machine contacted manufacturer servers daily for license verification with 72-hour grace period before automatic shutdown if internet connection failed. Cloud storage for programs added $800 yearly. An ISP outage meant production halt regardless of the machine's mechanical condition. American machinists in 1900 built shapers that cut steel all day because they understood a principle modern engineers forgot. Systems that depend on nothing external can survive anything external. Modern CNC requires electricity, software, networks, vendors, subscriptions, and luck. Shapers required electricity and a machinist. The precision problem of 1900 was solved not by matching European measurement infrastructure, but by building machines that made measurement irrelevant during production. Today's precision is solved by adding layers of digital complexity. Yesterday's solution still works in shops where 80-year-old shapers cut parts to 0.002 inch tolerances, while CNC machines await $6,000 circuit boards discontinued 3 years ago. In 2024, a 1935 Cincinnati shaper sold at auction for $12,000, 4 times its inflation-adjusted original cost. The 1995 CNC machine beside it brought $400 as scrap metal. The market had spoken. Permanence has value. Obsolescence has cost.